Problem statement. Imagine you have developed a COVID test. Sometime this test it says someone is infected when they actually are not infected. In other words, it gives false alarm. And sometimes it says someone is not infected when they actually are infected. In other words, it misses the real cases. Both are mistakes, but of different kind, and these are represented by alpha and beta. So, how much risk of being wrong are you willing to accept? Second question, how would you define the above risk in statistics? And the third question, which is the most important, is among the type of risk, alpha and beta, how would you decide which ones to use? Should you use alpha or should you use beta? This session is about answering these types of questions. So, when we do hypothesis test, we generally follow two steps. Step number one is we start with two statements about the population. You have null hypothesis, you have alternative hypothesis. Your null hypothesis, denoted by H0, is this that there is no effect or no difference. For example, the new drug has no effect on the population. That could be your null hypothesis. Your alternative hypothesis, generally denoted by H1 or HA, it would say something like this that there is an effect or there is some difference. For example, the new drug works better than the old one on the population. So this is your step one. Then you do your step two. We collect our sample data, we run a test, it could be t test or a z test depending on your conditions, and then make a decision. And your decision could be either reject H0 or you fail to reject H0. Based on these decisions, there are four different scenarios that are possible. So these are the four scenarios. You reject H0 when your H0 was actually true. This is called type 1 error. You reject H0 when your H0 was false. Well, that's a correct decision you made. All right. Then you did not reject H0. You do not reject H0 when your H0 is true. In that case, you made a correct decision. This is a correct decision. You do not reject H0 when your H0 is false. In this case, you made an error over here. This is a mistake you made. This is called your type 2 error. Now, the probability of your type 1 error is denoted by alpha. Type 1 error occurs when you reject the null hypothesis when it is actually true. It is another name for that is false positive. You conclude that something is happening when it really is not happening. For example, a person testing positive for COVID 19 when he is actually not. So, this is called false alarm. Alpha in this case is called the significance level, and you choose this level before you conduct your test. Commonly used values are 0.10, 0.05, 0.01. This is the more common ones among these three. Now, if you set alpha equal to 0.05, what you are saying is this that hey, I'm okay with being wrong 5% of the time when I say there is an effect. That is the essential meaning of when you set your alpha equal to 0.05. Now, let's try to understand your type 2 error. The probability of type 2 error is denoted by beta. A type 2 error, it occurs when you fail to reject the null hypothesis when it is actually false. This one right here, this scenario. It's a false negative. So this is your false positive, FP, and this is your false negative, FN. You conclude that nothing is happening when something really is happening. For example, a person testing negative for COVID 19 when he is actually positive. In other words, this was a missed case. Now, if I set, or if let's say beta equal to 0.20, what you are saying in essence is that, hey, I'm okay with being wrong 20% of the time when I say there is no effect. In other words, there is a missed detection. Now, when you set alpha equal to 0.05, let's take this value, and beta equal to 0.20. By the way, these two are very commonly used. You are saying, in essence, that I accept a 5% risk of false alarm of type 1 error. This one right here. and a 20% risk of missing a true effect. In other words, type 2 error, which is this right here. Now, alpha, this is chosen by the user. Beta, on the other hand, this is dependent on the size of your sample n and the population variability. Population variability in this case refers to population standard deviation. So, as the size of your sample increases, your beta decreases. In other words, your type 2 error goes down, which makes sense as your sample gets bigger and bigger, it almost like close approaches your population. The value of your estimate will come very close to your population. As your standard deviation, as your population standard deviation sigma increases, your beta also increases. In other words, your type 2 error also increases. Again, this makes sense because if you look at it, let's say this is your one distribution, and let's say this is another distribution right here. And clearly, this one, okay, you can see the width of this. This actually has a low standard deviation, and this one actually has a high standard deviation, right? This is sigma, let's say this is sigma 2, this is sigma 1. So when you pick up data set from here, it's very likely that it's going to be containing them in the true mean. Over here, because you have a high sigma, high variability, you can pick up data anywhere. So you will have high type 2 error over here. For the most part, users do not have direct control on beta. Then there is another term called power of test, which is denoted by 1 minus beta. This one, it measures the probability of correctly rejecting a false null hypothesis. In other words, detecting a real effect. Now, high power, which means generally close to 1, it means that the test is good at detecting true effects. So now through the problem. So imagine you have developed a COVID-19 test. Sometimes it says someone is infected when they are not infected. And sometimes it misses the real case. Both are basically are mistakes, but of a different kind, alpha and beta. So, how much risk of being wrong are you willing to accept? That's exactly what the significance level and type 1 and type 2 error helps us define in statistics. In this case, the amount of risk that you're willing to accept when being wrong is defined by your significance level alpha, which is the chance of a false alarm, type 1 error, and by beta, which is the chance of missing a real effect, which is called type 2 error. Now, when is alpha more important? In other words, in what scenario would you be using alpha? In other words, you want fewer false alarms. An example would be medical drug approval. You do not want to approve a drug that does not really work or is harmful. So, in this case, you have type 1 error and type 2 error. Type 1 error, it would mean that approving a useless or a harmful drug. A type 2 error would mean failing to approve a helpful one. In this particular scenario, in your medical drug approval case, your alpha is more important. Safety first. This is more important. So we're going to be following this right here. That's why your drug companies, they often use alpha equal to 0.01 or 0.001. So when is beta more important? You want fewer missed detections. So let's take a look at two examples. My first one is when disease screening test. Let's say your null hypothesis is that person is healthy and your alternative hypothesis is that person is infected. In this case, your type 1 error is going to be a false alarm, meaning healthy person has been flagged as having a disease, as having an infection. Type 2 error in this case would be a missed case where an infected person was not detected. So, which one is more important in this case? Well, missing a real case can be deadly. So, in this case, your beta is more important. That's why early COVID or cancer screen tests are designed for high power, low beta, even if your alpha is higher. So here you will be you will be actually choosing beta as a high priority over your alpha. Another example would be your quality control in manufacturing. Let's say your H0, your null hypothesis, is that machine is producing within tolerance, that the machine is working fine. Your alternative hypothesis is that machine is faulty. So here, your type 2 error, which is beta, which is letting defective product pass, this can be costly. It can be very dangerous. So in this case, my beta is more critical. So I'll be choosing beta. I'll be actually focusing more on the beta over here. Now, in what scenarios would you take a balanced case, like for balanced scenarios for alpha and beta? Well, these are the type of cases when both types of errors are equally important. For example, routine scientific studies. In this case, your researchers they typically choose your alpha equal to 0.05 and your power or your beta equal to 0.20, so your power comes out to be 0.80. So this one balances being too strict, in other words, missing effects, and too lenient, which is a false alarm.